Okay, good morning, everyone. Well, I say that, I can see 7 of you. 8 now, that's good. Numbers are going up. Right, so, okay, so welcome to your favourite lecture of the week, Friday at 12. So, let's see where we got to. Okay, so at the end of the last session, I started introducing this example of how to design a system. And we briefly looked at the problem, which was how to detect when there was air in fuel and how we can design an instrumentation system to make this happen. And we stopped fairly shortly afterwards, and by that point in the lecture probably most people have lost interest anyway, so we'll just recap that. The reason why this is important, it's important because first of all it's an interesting use of some of the techniques we've looked at for a real system that was built. But it's also important for how you would approach the coursework that's associated with this module. So there will be a coursework. I haven't published it yet because we don't really know enough to be able to address it properly. But this style of system definition of how things work is something that's going to be important in that, because it is a definition of a system and then solving that problem with the techniques that you'll have learnt throughout this module. And if we finish this example a bit early, I might introduce you to the coursework because you probably want to do a bit of background reading on it to understand the problem. As you'll begin to realise, understanding the problem for a lot of these engineering problems is most of the battle. And then when you understand what's actually required, then you can start to say, okay, now I can put together a system to actually measure this because I now know what's important. Okay. Of me, fed up looking at me. Right. So just to recap, a quick recap on the problem. The problem is that we want to know how much fuel we're buying from a petrol pump rather than buying air. Because if the tank gets empty and the pump starts to pump air or frothy fuel, you're buying air, and customs and excise take a very dim view of that kind of behaviour. So it's very important that fuel pumps are accurate, and one of the things that stops it being accurate is air going into the system. So how do we come up with a system that can measure the amount of air? Or one of the ways we could do it is with capacitance, because we can make the fuel act as a dielectric between two plates of a capacitor, and if you've got air as a dielectric, you'll get a different capacitance from compared when you've got fuel as a dielectric. This only works because fuel is non-conductive. But that's what I'm saying. Know your enemy, and then you can start to define what will work and what can't work. And then when you've got a list of things that will work, you can choose the one that's the best. So you'll all probably have done this, or you should have done this for your Part 3 projects, to identify what the problem is, and then what's the best way of solving it, given some options. Some of you may have been given options, other people may. If you're doing a project for me, you have to come up with your own options, and I help you choose which is the best. Okay, so in this case what we do is we will compare this against another capacitor, and in this case this capacitor will have a guaranteed sample of fuel as its dielectric, because this allows us to create a differential system where we compare two capacitances against each other, and any errors introduced by, say, temperature or the type of fuel changing or whatever become a common mode signal that we know with the differential system we can then ignore. So we're starting to apply some of the techniques that maybe we've heard about. So we came to this. We were given a specification for our measuring system. It needs to be a DC output, accurate to 2% or less than 500 microvolts, whichever is the greater. And the reason for that will become apparent later. And a transient response time, which means how quickly does it respond to a change, of 0.2 of a second. And we discussed this as being if a bubble travels through this plate here, it's going to take, well, we're assuming a maximum time of 0.2 of a second, and therefore we need to respond in that time to actually see the bubble. We don't want a bubble whizzing through here and us not being able to respond quick enough to see it. So that's what's been given to us. And as I've said, we will look at this with a differential type measurement, and one potential solution would be to use a capacitance bridge. So this is a bridge system, and we have to, because it's capacitance, we have to drive it with AC. So these are AC sine waves, and we suggested that we could drive it with an alternate phase. So if this one was going up, try and draw like that, a sine wave like that, the one down here will be in antiphase, so it will be going down and then up, and they would sum at this center point, and we would get 0 in an ideal world if everything was balanced. When these capacitances go out of balance, we would end up with some kind of residual, and the amplitude of the sine wave seen at this point would then become the amplitude is proportional to the imbalance of these capacitances. That's the idea. Right, so how do we implement that? Okay, that's basically saying everything that we've already said. So we would probably use a charge amplifier because we're trying to measure change in capacitance, and capacitances store charge on themselves. So if you look at this part here is our charge amplifier. So this resistor would be maybe not so significant in terms of the fundamental operation of the system. So if we ignored that resistor for the time being, but we understand we need it for bias currents and things, we would see that we've got a feedback capacitor, which is similar kind of size to the ones we've got here, and we would expect this to be effectively a charge to voltage converter system, which is great. And if we apply, we've got a virtual ground here, so if we apply superposition to these points here, we can say that the output voltage here is going to be equal to whatever the voltage is across, or whatever the current flow through this, what current going in is equal to current going out, is what I'm trying to say. So we'd end up with this equation, C minus C V out, so the voltage across, or the current across this, current through this, is equal to the current going in here, which is going to be equal to, by superposition, so suppress one of these and work out what's going on, suppress the other one and work out what's going on, you end up with C2 V2 plus C1 V1. So this is C1 and C2, and this is V1 and V2. So this is the current here has to go through here and maintain the 0 here, and then the current here has to go through here, come out through here and maintain a 0 here. So this is the superposition equation. So if you then say, I will make V1 equal to minus V2, i.e. these are in antiphase of each other, and we just call that V in, we can then say that we end up with minus CV out is equal to C2 plus C1 times V in, and if you manipulate that through, we end up then with V out over V in is equal to C2 minus C1, the difference of these two capacitances, over C. So that's just, so as this difference changes, the output will change. So if you let this change in capacitance just be called delta C, so C2 minus C1 is delta C or whatever, then V out over V in becomes delta C over C. So if these capacitances are the same, so there's, in our case there's the same amount of fuel in each one, the delta C will be 0, and we'd find out that V out over V in is equal to 0 over C, which is 0. As the capacitance changes, this becomes non-zero, and we will get an output. So that's simple analysis, gives us a clue what's going on. So you can then just check this by simulation if you're not happy with how that works, or you're unsure that you've got the maths right. And so we put it into the simulator, put some example circuit values in there. I've chosen a real op-amp in this case. You can use an ideal op-amp out of LT Spice if you want to. So I've put in a real op-amp. It's a good one. It's got FET inputs, so its offsets are not are very small. And then you can see that if I run the simulation for delta C's of 0, so the capacitances are balanced, and then slightly out of balance, and then quite a lot out of balance, because this 0.5 nanofarads is half this value, this reference capacitance. You can see that for 0 we get nothing out, the orange line. For 0.1 we're starting to get a sine wave out that's smaller, and then for 0.5 we're getting a bigger one out, and the scales match up with the basic equations. So that gives us good indication that this measuring system looks like it might actually work. in terms of being able to measure a change in imbalance of capacitance here. So we haven't tested it fully, but we've just verified that the basic idea works and the values are reasonable. So I said that we chose a good op amp there with little offsets. You might ask the question, well, how good does it need to be? Because cost is always an issue with these things. 741s are quite cheap. If we use the 741, would it work? So if you simulated it with a 741, so we just take the previous example and replace this LT1037 expensive op amp with a 741 cheap op amp, does it work? And the answer is, well, yes, it does still work. But now we get significant offsets, because now we're offset at around about 0.8 of a volt rather than the 0 volts or close to 0 volts that this good op amp gave us. Right, so there's the significance of know your op amp. But that may or may not be okay. It depends on what we do next as to whether this is okay or not. So if we AC coupled this to the next stage, this would remove the DC offset, and we would be okay still, as long as we've got enough headroom in the power supply. But so in either case, op amp, whichever op amp you chose, the amplitude of the signal gives us a measure of the difference in capacitance. But we still have to turn this AC amplitude into a DC level. But we're mindful now that maybe there are some offsets that we need to be concerned about. So what we would probably do beforehand is do this sort of thought experiment about how we would approach this problem. So we know that we're going to use a charge amplifier, and we know now we've got to turn it to DC and do some other stuff to it. So let's build a prototype system diagram, put it into block form, so we can break the problem into little chunks and then see how the sort of signal flows and what we get. So we know we've got to have a sine drive, but well, we'll call it an AC drive. So we're going to be driving AC into this signal, so we need something to generate our AC driving signal. And then we're going to go into this sort of differential charge amplifier system, which is going to give us an AC output, which is proportional to the difference in capacitance. And then we want to get a DC out, so perhaps we need to have some form of rectification. We need to turn the AC into a DC. There's a good chance there's going to be some filtering needed, because I can't see it being completely smooth, so it's best to assume that it's not going to be. So we have a filter, and then we probably want to have to scale that to give us the output values that are required, so there'll be some amplification going on, and then there'll be some form of output, which might be a meter or a display or a feeding into a computer system or something. So this is our sort of prototype system diagram in rough terms, and now we sort of have to just define what goes into these blocks, what the levels are going in, what are the levels coming out. And this is the sort of thing that I want you to do in the coursework for the problem that is going to be cropping up there. Produce a system diagram showing how the architecture is constructed, or what your architecture is, and then you need to tell me what's in these different blocks and give me some evidence that you think they're going to work properly. And we'll talk about that as we go forward. Right. So that's where we got, and we've got these constraints that this system has to reply to. So we should proceed with the intention that we'll have to build this circuit eventually, and then maybe even sell them. So we need to keep one eye on practicality as well of our systems. So rectification. The next stage in our block diagram is to rectify this somehow, because we know we've got an AC signal coming out that we need to turn into a DC. If we use standard diodes, because diodes are probably the most straightforward approach for doing rectification, we will maybe cause ourselves some problems if we approach this naively, because a diode needs about 0.6 volts to turn on properly. So if the signal coming out of our charge amplifier is less than 0.6 volt, we won't even start to rectify it if we just used a basic diode rectifier. So given that we're going to like to be dealing with small signals, we need something a bit better than a basic envelope detector that you might have come across with a diode. So once again, op amps can come to our rescue, because we can build what's known as the precision diode. And this is quite neat. It uses a virtual earth principle to keep the voltage across the diode in the feedback loop at 0. So effectively gives us a turn on voltage of 0. So this is sort of, again, know your enemy. Put a diode in the feedback loop, and you end up with a working system. So this would be the equivalent of a full wave rectifier involving 2 diodes and a few op amps. There are other ways of doing it. This is just one that works quite nicely. So, you know, first thing you have to understand is, what's my problem? My problem is I need rectification. The second thing is, how do I do that? Well, probably precision diode is what I want, because I don't want this 0.6 volt offset. And you just have to know that precision diode circuits exist, and then you can start looking them up to see what might be a good starting point. You might find there are 3 or 4 different precision diode circuits, and then you have to sort of assess them to see which one is the most convenient for your particular solution. So we're starting at an architecture level and then working down to sort of component level. So if you're interested in how this works, I'm not going to spend a great deal of time running through this, because I will just get it wrong and confuse everyone. It's better that you just look at it and see what's going on. But basically what we've got is a sort of an inverting amplifier and a non-inverting amplifier, and one of them is turned on for one direction and one of them is turned on for the other direction, and then the outputs are just added. So there's enough information on this diagram for you to follow it through. It will take me a long time to try and explain it, and I will get confused and you will get confused. So I will let you think about this and work through the working as we go forward, in your own time. So I've been quite detailed about it, because I like to have a lot of detail on these things. So you can see that so I've done a slide for positive inputs and a slide for negative inputs, so you can see which way the various currents are flowing. And what's going on is saying that these resistors are not really in the loop. It's because the potential across them is 0. So there's some subtlety there. But it all works on the basis that you've got virtual grounds operating in these op amps. Okay. Output is always V out equals V in, or for the previous slide, the output it should be equal to must be equal to minus V in, I think. Okay. So again, you can simulate that. And I've simulated it here with a 741, so I've put a sine wave in, and the output I'm getting now is a rectified, full wave rectified sine wave. Yeah, so the negative part of the sine wave has been flipped up and has come out here, and you can start to see with the 741 you start, and this has been done for small signals, 100 millivolts, so we can see that it actually works for small signals and bigger signals as well. But we're starting to see some issues at these points here. Every half cycle we're starting to get what's called a crossover issue, so it's not completely symmetric in what's going on. So that's something that's going to introduce some errors, particularly at small amplitudes. So let's try with the better op amp. So we tried the better op amp. Gives a little bit of improvement, but we've still got this problem, so it's not really down to the diode system, I would suggest. So the error there has probably come from the input stage still, which is our capacitance system. So you have to go back and then start playing around to see what's going on. But if you use a 741 as the input stage, the giant offset that you get there results in no rectification under these circumstances at all, because we had a 0.8 of a volt offset, remember. So that's something to bear in mind as well. Yes, I'm not quite sure what we're saying there then. So if we conclude that we can use either 741 or any other op amp for the rectification in this case. We can, that's true, if we AC couple it. So that's probably the thing that's missing there. So remember, if we AC couple, we DC block, and then it all works nicely. So once we've got that, we need we've got effectively a DC waveform, because the waveform that we're getting has a DC average, okay, but it's not smooth. We've got a bouncing signal. And we'd like to have a nice DC flat level, so we need to work out what's the average of this waveform and get that out as a signal. And one way of doing that is to filter it, and the simple way of filtering this in this case, we're going to do filters in the next part of the course, proper ones, but sometimes you don't need to do that. So what we would do is we will just average the output voltage across a big capacitor in this circuit. So we've added a capacitor in here, and that's will allow us to average the circuit. And the average of a rectified sine wave is well known to be 2 V peak over pi. And so if we've got a peak of 0.5 of a volt out of our rectifier circuit, we would expect to, by applying that, see a DC level of 318 millivolts. And we can carry on working that down. So there's going to be some scaling factors required. And this is important. We'd expect to see 0 for 0. 0 volts in, 0 volts out. So if we simulate that circuit here with our waveform coming in, so we're just doing these bits at a time, we would see that what we actually get then for the three cases are 314 millivolts if you measured this accurately. And remember, we were looking for 318, so we're 4 millivolts off, so it's not bad. 61.93 millivolts for the other one. I forget what it was now. Input of 100 millivolts, so a peak of 100 millivolts gives us an average of 63.7, and we actually get from the simulator 61.93, so again we're not far off. And then for 0 in we get 0.8 of a millivolt out, which is, you know, not bad. But then we have to go back to our spec, and it says this meets all the specification apart from the absolute error being less than 0.5 millivolts, as the other two are only in error by 1.4%. So these two here are small errors, they're less than 2%, so they're fine. But remember, we had to be less than 500 microvolts or less than 0.5 of a millivolt, and 0.802 millivolts is bigger than 0.5. So this is where that part of the spec starts to become important. For very, very small signals, the absolute error becomes the dominant one rather than the relative error. So we've got to do something about this 0 in and 0 out business, because we're not getting 0 out, we're getting 0.8 out, which, although it's not much, it's outside the spec. So where does this error come from? Well, off the top of our heads we don't really know, but it's most likely due to offset errors, imperfections in the input amplifier, because we've pointed the finger of suspicion at that already. But we've been operating at 5 kHz, which is something I neglected to tell you, but the spec didn't tell us what frequency to operate at, so I just chose a frequency to start with. So we've got that parameter to change. We can play with that if we wanted to. With op amps though, we've seen that they can struggle at high frequencies due to the virtual earth starting to fail. So maybe without any constraints that have been given, we're free to choose whatever frequency we like, so maybe operating a lower frequency will be better for the op amp and give us a better virtual ground. Maybe that works better. A disadvantage of a lower frequency though is it will lengthen our response time, because things are just working slower. Our target is 0.2 of a second, but if you've measured it in the simulation you'll find actually we're down at 0.05, so we're actually all right really at the moment, so we can afford to go a bit slower. So I did that, and actually it makes no difference if you go down to 2 kHz or so. So there's no advantage in going slow in this case. But the advantage is in the simulator you can try these things quite easily and see what the answer is. In a circuit, building it becomes a bit of a problem. It takes a lot of time. So the input stage is probably all right. Let's look elsewhere. So we look to the rectifier stage. We've used 741s. Maybe if we move to a better spec amplifier, we can improve matters. We sort of said we were okay 741s earlier, but now we've got these new problems. Perhaps we have to go back. So we swapped the 741 for a different op amp. And you can pick anything you like really. You just got to. There are over 3,000 op amps in the catalogue, so you've just got to know what it is you're looking for. So I chose a 1055 with low offsets, FET inputs, and now we get 315.7 millivolts for our simulation, 62.7, and now 2.5 femtovolts for zeros in. So that's an error of 0.7, 1.4%, and hardly worth measuring. So although we concluded earlier we could use a 741 for the rectifier, it turns out that the zero offset spec is quite tricky and we still need a better op amp. So this is an indication of all the different parts of the system can interact with each other in ways that weren't immediately obvious when you first started building it. So don't be afraid to go back and reconsider things or try and chase errors down using a simulator, or even building parts of the circuit and just trying them out. Okay, so there is some ripple on the top trace. Probably can't see it, but there's a very small amount of ripple. I'll emphasize it here, which means that we haven't perfectly filtered it. We can reduce that by increasing the size of the filtering capacitor we put in. But again, with a bit of prior knowledge, depending on the accuracy of the following A to D converter, we may not need to worry too much about it, because increasing the capacitor, although it makes it smoother, will add some lag and slow the system down. So that might be something that we're particularly worried about. But you can see here that our system is responding very quickly at the moment. Right, so at the moment we're getting 314 millivolts out for our maximum input size signal. We need to amplify this because our spec said we wanted 1 volt output for full scale operation. So we need to build an amplifier that has a gain of 3.16 to get the required output. So to get it right, you may have to, when you build it, build a potentiometer into your feedback resistor just to make sure that it's tuned properly. So that's something to bear out if you're designing the circuit. But you're going to have no trouble in meeting the spec with that. The gain of 3.16 is quite low, and it should be easy for any op amp to achieve. So we can amplify in our circuit by either adjusting R5. Where's R5? So this one here, the overall gain resistor, in the average summing amplifier stage, or we can just add a non-inverting amplifier to the output if we wanted to. So the output of our system, we could, well, what we've done here, we've just added one. And so now for our 3 test input signals, we're still getting out something close to 0, 0.2 volts for 100 millivolts in, and 1 volt out for our 0.5 changing capacitance. Okay, and if we zoomed in on the ripple that I was talking about earlier, you can see that on top of this signal, this 1 volt signal, there's a small amount of ripple. And small is a definition that's relative, so we'd have to do a little bit more work to work out if this is too much ripple or we can accept it, and that depends on the what happens next in terms of the resolution. If we're driving a meter, this isn't going to be seen, and if it's a low resolution A to D converter that's taking the signal, probably not important either. Right, now we just have to remember that this is using perfect sine wave generators at the input side. So we have achieved our specification, but we have assumed a perfect sine wave and a perfect differential input with no phase differences, or 180 degrees of phase. And this is actually tricky to achieve, so maybe consider some less taxing options for generating. We could use any waveforms for the original equation for the charge amplifier, as long as they're symmetric. Because they just all cancel out and we haven't been constrained by the spec. So perhaps square waves could be used because they're relatively easy to generate. Sine waves are very difficult to generate. So let's try by driving our final solution with square waves rather than sine waves. So we'll just, instead of having a sine wave input in our simulation, we'll just change it to a square wave input. We get our out of phase one just by amplifying the square wave by -1, and then if that works, to generate this we can use something simple like a 555 timer, which is good for generating square waves, so our frequency generator, or we could even just drive it straight out of an output port of a microcontroller at these low frequencies. So you can start to see how we then have to consider the rest of the system as well going forward. So here's our square wave generator going on in here, and our inverting amplifier. So here we've got alternate phase square waves, we've got our charge amplifier system, and we've got our precision diode amplifier and filtering circuit bolted on the end. And that's more or less what our sort of initial prototype circuit looks like, and if that works okay, then it's relatively straightforward and cheap to build this. So if we run this at 5 kHz, we get results that are just within our specification, and you can start to see there's a little bit more ripple on this top trace. Probably can't see it, but it's there. The zero input spec is marginal, as it goes from 246 to 252 microvolts, and this will have to be amplified because the output for here is only 500 millivolts, so to get that up to 1 volt we've got to put it through an amplifier with a gain of 2 in this state, because the average is no longer 2 V peak over pi. So if the error here is 246 microvolts, it gets doubled in the amplifier, so we're getting quite close. But the other ones are all fine. So if we want to give ourselves a bit more margin, we have to go back and investigate this zero offsetting in a bit more detail. And one thing we didn't look at was the starting values of the or the gain, if you like, of the charge amplifier. So we could play around with that a bit. We only chose 1 nanofarad as a starting point, so we can try decreasing the gain a bit by increasing C to 2 nanofarads. If the offset's coming from here, that will reduce the offset. And it turns out that that works quite nicely. And that moves the zero input down a little bit, and it gives us just enough to be inside of our spec. So our output now for our full system is going to be 470 microvolts, and the other outputs end up with an error of 1.18 and 1.5%. So although it's tight, we've managed, with a bit of thought and a bit of intuition and a bit of experience, to get it to a point where we've got a nice simple way of generating square waves, a relatively simple instrumentation system. We're going to have to spend a bit of money on posh op amps for it, and we could go and investigate these in a bit more detail if we wanted to, but this meets our spec. If we look at the settling time of this system now, so we do a step response on it, and we can see it responds quite quickly. We wanted it to respond within 0.2 of a second, and you can see it responds quite nicely, even at the worst case, and gets to 0.2 with time in hand. So if we wanted to, we could start investigating reducing ripple and increasing the speeds and everything like that. So we end up with the final circuit, looks something like this, and this could be our starting point for working the system. In practice, you might find there's imperfections and things that start to introduce some other errors, so there needs to be a bit of investigation into that when you actually build it, because not all circuits are the same when you build them. And it may well be in this case you have to go back to the customer and say, look, your 500 microvolt spec for a zero input is actually really tight. Maybe you can relax it a bit. Otherwise, I'm going to have to spend a lot more money and making this system perform a lot better. And if that spec turns out to be just something they've written down because it was a good idea at the time, by changing that spec you can actually increase or decrease the cost of your system. So it's important to get the specification right. If you make it too hard just for the sake of it, prices go up, and cost is always important when you're designing circuits for customers. And there's all kinds of stuff here. So once a microcontroller is introduced, because maybe this is going to be part of a microcontroller system now, then it becomes possible to consider other solutions, and with a bit of knowledge you might say, well, synchronous demodulation might be a way forward, and I won't then have to average that AC waveform. Or we can just be very careful when we trigger an A to D sample. If we're generating our driving waveform on a microcontroller, we know when it starts and when it stops, so we can just sample at known times in the cycle, and therefore maybe we don't need to worry too much about making a nice smooth output. So there's all kinds of stuff you can do, but what you've got to do is stop somewhere. And once you've got a solution that works and meets the specification, it's time to stop, because if you just keep going, you're costing money, and that costs you profit. Customer will be very happy if you keep iterating, but eventually he'll get bored as well, because you'll keep saying, just give me another week and I can improve it, and it doesn't need improving because it meets the spec. So it's important to get the spec right, and it's important to design to the spec, and it's important to go no further. Okay, so you can just keep going and going and going with these kind of systems. So what are we trying to solve here? This is saying, well, actually, if we AC couple the 741, remember there's an offset here, so if we put a capacitor in here and we block that offset, that gets rid of all the offsets, and maybe that's a good way to do it. So we can try a similar 741 again, and we can, because this is a cost reduction exercise if it works, put another capacitor in there to block it, and then see what happens. Does it work with the square wave solution? Sort of, but we have to then be much more careful with the filters at the output, as we will see. So here I've had to actually put a second order filter with a 1 kHz cutoff frequency in here. It's been designed properly. So we've added a bit of cost here, we've taken away some cost here. Have we improved the performance? Maybe we have. So you can just see that it just goes on and on and on and on. Not much more to say about that. this works, why go any further? But some of you will be going, well, I want to go further because I want it to be neat, I want it to be the best. But the reality is you want it to be good enough. So we can say what our final prototype system looked like. We've got a square wave drive where we had a sine wave to start with. We've got our charge amplifier block, we know what's in that now. Rectifier, we know what is in that block, we know what has to go in, and we know what comes out. We've got an averaging block which is actually included in our system in the circuitry for the rectification, but it's a separate function. And then we amplify and filter it to get it to the right size, and the amount of amplification needed depends on whether we had a sine wave or a square wave drive, so it all links back. And then we've got our output coming through, and our output we've tested. We've got a full scale of 1 volt because we scaled it properly, and we've tested the accuracy, and we're inside the accuracy, and we're inside the response time as well. So that's sort of an approach to how you might design these kind of systems. So in summary for that then, the specification is very important for a problem, and if you take nothing away from this other than that if you specify it correctly, then when you build to that specification it will do the job. And the better specified something is, the more chance there is of it being fit for purpose, which means you need to consider the problem you're trying to solve and then come up with a specification that matches the solution to that problem. And you don't want to make the specification too difficult to hit, because that just makes life difficult for everyone and eventually makes the solution expensive. But if you make it too vague and woolly, then chances are when you've built this thing it won't completely do the job you're interested in, because you didn't define the job properly in the first place. So this becomes a really important part of any engineering project. So you go through the design cycle, you can keep iterating, you can keep refining, do it in chunks, and then look at how you can do cost reduction or simplifications. Things only need to be as complicated as they need to be. Simple is best. And then you can start to see how you might develop these things going forward. So you can type this into LT-Spice and have a play with it if you want to, if you've got time to do that, but probably you haven't. But it's a similar kind of solution that then follows for the coursework. Right, so I'll discard that. If we then quickly have a look at the coursework exercise, just to give you an idea of what I'm going to be expecting for that in the last few minutes or so. It's nearly finished. There might be just a couple of little edits, but fundamentally it's the same. So I'm looking for 2,000 word equivalent, and bear in mind, I would say this again, that you can't do this at the moment. All right, you don't know, haven't got enough knowledge, not from my course anyway, to do this. So don't start thinking I can do this now. But what you can do is you can start doing the background on understanding radar, because it's going to be a CW-FM radar, and I'm guessing that none of you know what a CW-FM radar is at this moment. So we're starting from a level playing field, and it's allowing you to understand the problem, define the specification, and then work up a solution like we've just done, using a lot of the tools and techniques that you will learn in this module going forward. We've done some of it so far, but there's other stuff to happen. So this, 5th of May is a long way away. But, it doesn't hurt to read it up in advance. It's worth about 20% of the module, and so you should be expecting to spend 25 hours or so on it. So you're not going to rush it at the last minute. The aim of the exercise is to allow you to have some freedom to design your own specification to solve a problem, and then design a system to meet that specification using functions discussed within the module. Okay, and I'll give you some clues and help on what the system looks like. So the overall problem we're trying to solve is that someone's designing a robot, and part of the specification for the robot is that it needs to be able to detect objects nearby, in front, up to a distance of about 5 meters or so. Okay, and you can see that will be a sensible thing for any robot. It wants to know what's around it. So this system should be able to detect range. It needs to be able to know how far away an object is. It's not too fussed about direction, because the robot can turn around, so we're going to be interested in just range. The design team have decided the module should be based on an ultrasonic principle, so an ultrasonic radar module is to be designed. So we're starting to get some constraints. We have to work within these constraints. So further, it should be based on the FMCW principle, which is frequency modulation continuous wave, which sounds complicated, but it's not that bad, and I'll explain it to you in this document anyway. And we're going to use something called triangular modulation, and again that will be explained. So the interesting thing for you is the output from the radar module is to be an 8-bit digital word representing range. So I'm allowing you to use a microcontroller to do basic processing, but it won't have enough capability to do high-speed digital processing like FFTs. Therefore, all processing of the radar signal needs to be done in the analog domain before it goes into that. So I'm constraining you. Okay. You cannot assume that the micro has a built-in A to D or D to A converter, so I'm wanting you to create one of these as well. But I'm not expecting you to provide any code for the microcontroller. I just want you to tell me what it's got to do. So, for example, you might want it to provide a control signal for the micro. So you just explain what the control signal is, when it should be generated, and why you need it. So what we're interested in is what's in this red box here. So we've got a transmitter and a receiver, which I'm I'm going to assume that you've been given. So you don't have to worry about how it's actually generated. You just assume that you can generate an ultrasonic wave. TX means transmit, so you're going to be transmitting a wave. It's going to be bouncing off a target and coming back, and you'll be receiving it. And then once you've got a received signal, you need to make some assumptions about it based on what was transmitted, and then you design what's in this red box, which is some analog processing and an analog to digital interface, so this mixed signal idea. And then that gets fed to a microcontroller, of which you're just interested in this interface. You're not interested in what's in the microcontroller. Right, so there's some instructions. Decide on a specification, e.g. maximum range, which if you were listening is 5 meters. A minimum range, that hasn't specified, but there's going to be one, so you need to worry about that. Response rate, how quickly does it need to respond? Is once an hour okay, or is it going to be once a second? Accuracy of distance, etc. And just give reasons for your choice of specification. So you're free to decide what are the important points that you think are necessary here, and just put a few words down to justify them. And there's some clues about speed of sound there. And used in description given below and other sources, describe the triangle modulated CWFM architecture in a system diagram form, which is what we've just done. You know, the blocks with the sine wave and the filter and the amplifier, that kind of thing. And then you can describe the function of the various blocks in your system diagrams, so we know what's going on. And link this, that's an edit I've got to do, to your specification from above. And then basically just check that it all works properly and give me some indications that it's working. So, but you can do it by simulation. You can simulate just individual blocks and check they work okay. Some of you might want to simulate the whole thing, which is a bit of a challenge, but it has been done. And then criticize your solution and make suggestions for improvement. Right, you do not need to produce a device level design that is fully simulated. You should produce a system that is analyzed at behavioral level, which is a block diagram level. For example, if you decide to use a phase lock loop, this will just be a block in the system diagram, but then you need to tell me what's in that block, what goes into it, and what you're expecting out, and then some details about the design features of the PLL, which you won't know yet, but there'll be things like this. Okay, so I'm not expecting you to go down to the transistor level, build a PLL and simulate it. Okay, so there's some instructions there. So really, what you need to understand is radar, and so there's some words in the document here about radar, and I'll publish this document shortly on the web page. And so for a pulse radar, you just send out a pulse. It takes some time to travel. It's all about time. Hits the target, reflects, and comes back again. And you just time the difference between the transmitted pulse going out and the received pulse coming back. And then the distance becomes the speed of sound divided by twice the time difference between it. So that's a simple pulse radar. Doesn't give you much information really. So you can start to see you can build a block diagram to define this kind of system. So that's just crude measurement. It's not that accurate. Works quite well. Another way is to use phase measurement. So you can transmit a continuous signal. So this is one cycle of a continuous signal, but it will be continuously transmitted all the way along. It hits the target, a signal is reflected, and the reflected signal will arrive at a certain time delay and will therefore have a different phase So this phase difference between the two will remain constant. If you measured that phase difference, you would have some indication of the delay, and by knowing the speed of sound you would understand the range of the target. But this is only unambiguous up to a range of one wavelength. Once you get a delay of more than one wavelength, you can't tell how many whole wavelengths there were. It's a sort of a modulus thing. So in the case of an ultrasonic radar for use in air, it's a small distance, 40 kHz with a speed of 330 meters a second. The range is 8 millimeters, which is the wavelength. So that might be good for measuring a small vibration. And some of these radars are used for actually sort of measuring breathing rate from someone. So if you aim the radar at someone's chest and it moves up and down a small amount, you can actually measure that distance, and from that you can calculate their breathing rate. So that's the sort of thing that that's used for. It's used for detecting when babies stop breathing and that kind of thing. So FM radar is a bit more complicated. So we can see an evolution here. If we start to transmit a signal and we change its frequency continuously, so here the frequency is getting higher and higher and higher, when it eventually hits the target and comes back, the received signal will have the same kind of frequency shape as this, but we delayed. So the received frequency at a given time will be compared with a higher frequency that's going out, and so the change in frequency between these two becomes indicative of the time delay and therefore the distance. Okay. And it's usually drawn in a diagram such as this. Now the frequency can't keep changing the same direction forever, so eventually the frequency will start to then come down again, so you end up with a rising frequency and a falling frequency and a rising frequency and a falling frequency. So the transmitted waveform here is showing a rising frequency, then it gets to a certain point and then you get a falling frequency and then a rising frequency, and the reflected one will then follow that but with a time delay. And if you then measure the difference in these frequencies here, that's proportional to distance. Now you can see there's some confusion at the point when the the modulation starts to change direction. So this is triangular wave modulation. So you have to be careful about when you start to take the measurements. So you can only take sensible measurements when this gap is constant, so between here and here, and you can take it from here and here on the way down, but you can't really get anything out of this point here where it's all starting to fall apart. So there's some delays on this, but not too much. So that's great. That can measure distance. It's quite a clever way of measuring distance, but it cannot give any indication of velocity. But a moving target can give a false indication due to Doppler effects. So Doppler is equivalent of a change in frequency because of a moving system. So think of an ambulance coming towards you and then driving away, you'll hear a change in tone. So it's that kind of thing. But if you're measuring a change in frequency, and the change in frequency is introduced by the target actually moving at a velocity, then that will start to confuse your range measurements as well. Because all you're doing is measuring a change in frequency here. And if that change in frequency is due to a velocity as well as a distance, then suddenly you can't resolve between the two. So we have to think of a way of doing that, and that's when an FM Doppler radar comes in. So that allows us to get both range and velocity information unambiguously, and this is where it starts to get very clever. And if you use the triangular modulation, then you end up, as we've just seen, with a waveform that looks like this when the target is a fixed distance away and not moving. And this is called the difference frequency or the beat frequency. And as long as you measure in these ranges here, you actually can get an indication of what's going on. And we're interested in the magnitude of the frequency difference because obviously there's a sign difference here. And if you look at the change in frequency, or the magnitude of the change in frequency, you can see that in those regions you've got a fixed difference for a non-moving target. Can't do it in this bit, but as long as you know about this, it's fine. Right, but when the target is moving, there's a Doppler shift in frequency, which gives a false indication of distance. But the Doppler shift will be in the same direction, irrespective of the modulation direction. So even if you're modulating up, and then changing the modulation down, you end up with an offset in frequency that's always fixed due to the velocity of the target. And so you can actually extract that by using differential signals and common mode signals. So in this case, with a moving target at a certain distance, you can see that the reflected wave, the red line, is now changed in offset. It's got the same distance apart, but it's been changed in offset, which means this bit here that we were measuring before is now squashed up. But this bit here now is extended in terms of frequencies. So the delta frequencies look like this. I mean, it's different depending on whether the modulation is going up and the modulation is going down. And this difference is caused or is related to the velocity of the target. So then you can actually work out that by understanding this, the distance to target is actually the sort of average of these two differences in signal, and the velocity is related to the difference going on here. And so we can actually now separate unambiguously distance and velocity if we use this triangular modulation. So your job is to design a system that can do this. We're only interested in range. There's no specification for velocity, but you have to remember that the velocity will affect the accuracy of the range calculations. So you need to make the range calculation insensitive to velocity, which means you need to implement this type of system. You'll need to generate 40 kHz carrier for the ultrasonic transmitter, which means building an oscillator that will run at 40 kHz. And you need to modulate its frequency with a triangle wave, which means you need to build a triangle wave generator, which we'll talk about later on in the module. And you also need to build a voltage controlled oscillator, which has its output frequency controlled by this triangle wave. And then you need to decide how much to move away from 40 kHz, and then you need an amplifier to amplify the signal going out as well. Right, and there's various other things that you can probably think about going forward as well. So when it comes back, you need to amplify the received signal, so we've done amplifiers, demodulate it to recover the original triangle wave envelope, which I'm suggesting that the best way to do that is with a phase lock loop, so probably best you take my word for that at the moment. You then need a way of comparing this triangle wave with the current transmitted triangle wave, so the one that's going out, so we can actually measure the delay between it, and that will give you a measure of the frequency difference, so we can actually build a simple differential amplifier to measure that, and then we can that becomes a DC output signal that we can just measure, and that gives an indication of the velocity. And as long as we can detect whether we're up modulating or down modulating, we can then start to do some simple calculations and work out what's going on. Okay, you may assume, this is quite important, a single target is in range at any one time, or no target. If you've got more than one target, radars become very complicated, so we won't want to go down that route because we're not that interested in radars. We're just interested in the processing for a particular problem. So I've given you some more information on how things work in this document as well, and you're free to look it up for yourselves as well. But I will publish that, but you can't do the work just yet. Because we haven't covered all the aspects of the course, but what you can do is read through the background notes and understand the problem. There's nothing stopping you from doing some background and figuring out what it is that you actually need to do, and defining the specification for it. How you actually do it is something that will become apparent as we go further forward into the course. So I hope that was interesting enough for you. Next week we'll start a new part of the course where we start looking at filters, and then after that we look at power supplies and amplifier, other things as well. But yes, and if you look at the old website, in terms of if you go onto Blackboard and look at the opening page, it links you to the ECS notes pages, and on the ECS notes pages there are lots of slides and information and examples and other detailed stuff that I haven't spoken about for all parts of the module as well. So although a lot of this is going on to Blackboard, please don't forget that there's a lot of information on the ECS notes page which is linked to from Blackboard to make it easy for you. Okay, so see you next week.